Hello, Chem 2, and welcome to the second part of the ending of Chapter Two's sections. We're going to look at sections 6 and 7. Most specifically, we're going to look at the covalent naming and formula writing and the acids naming and formula writing. So the last thing we're going to do is predicting formula for ionic compounds. They're actually acids are ionic compounds, and then talk about how to do the naming. So let's deal with the first thing, which is covalent bonds. Okay. Now, covalent bonds are a little different, whereas ionic bonds were ones where we take a atom that has too few electrons and an atom that has too many electrons, and they come together in perfect harmony, and the one that has too many donates one or more to the one that has too few, and there's a transfer of electrons. That's a very, very common bond. But an even more common bond is a covalent bond. A covalent bond is one where the electrons are shared. Both atoms really, really like electrons. So what we have is a lot of nonmetals. The nonmetals will get together. And as a result of the nonmetals getting together, they will share their electrons between the two. So whenever you have something like CO2, C, carbon is a nonmetal. O, oxygen is a nonmetal. They're going to bond covalently. H2O, water. H is nonmetal. O is a nonmetal. They're going to combine together covalently. They're going to share electrons in such a way to make sure that they both get up to a full shell. So let's talk about how you name covalent bonds, because they're covalent molecules. They're a little different. And unfortunately, they pose a little bit of confusion because they're essentially too simple. Just like ionics, you're going to name the first element first, just like we did in ionics. Just like we did in ionics, you're going to name the second part or the second element with an IDE. However, where they are different is the last piece of the puzzle is you're going to add a prefix of a to indicate how many there are. Mono for 1, di for 2, tri for 3, tetra for 4. You're going to add a prefix in front to indicate how many of each one of those atoms there are. So it makes it easy. You don't have to worry about what's the charge because there is no charge. Now, there are some exceptions for the naming. First off, for instance, you know there's carbon dioxide. You don't say monocarbon dioxide. So the first element, if there happens to be just one, you do not put a prefix of mono on it. If the second one has just one, then yes, you do use a prefix of 1. So for instance, carbon monoxide has only 1 carbon. Second thing is you hear from the term carbon monoxide, you do not put both vowels together. It wouldn't be monooxide. It becomes monoxide. Whenever you have two non-I vowels, neither one is an I. When you blend together the prefix and the name, then you drop the first one. So tetroxide. It's not tetraoxide, it's tetroxide. Trioxide would be correct because the tri has an I on it. So let's look at some examples. So sp4. S is sulfur, P is phosphorus, which becomes phosphide, but there's 4 of them, so it becomes sulfur tetraphosphide. Second one, P is phosphorus, we already said that, it's in the front, so it doesn't get an IDE. O is oxygen, so for the second one, it becomes oxide, but there's 3 of them, so it becomes phosphorus trioxide. Phosphorus for 3 oxides. What about the last example? It's nitrogen, so it's nitrogen, but there's 2 of them, so it's dinitrogen. And oxygen, well, it's the second element, so it gets the IDE, so it becomes oxide. But wait, there's only 1 of them. The second element in a covalent bond always gets a prefix, so it becomes monoxide, so it becomes nitrogen monoxide. So the logic is you're always going to name using those prefixes. You're always going to name using the prefixes. It's different. You're not going to worry about the charges or anything like that. You're going to literally look at how many there are for each one of them and indicate how many with a Greek prefix. And here's the ones: di, tri, tetra. pentahexahepta, octananodeca. Okay? Here's examples that were given to you in your book. Okay? So water's real name is dihydrogen monoxide. But have some fun. Google ban dihydrogen monoxide. There's a whole bunch of really weird websites out there about the banning of water. It's more of a hoax to try to get you all fired up about all the really, really bad things that water does, if you think about it in a very propaganda-ish kind of way. Okay, so that's the covalent bonding. Now, why do I say it's problematic? Well, now it becomes really, really easy. And what I normally see, which is very, very wrong, is compounds like this, where it's like, oops, wrong. Let's see if I can get this to work. Like a compound like this, like we did in the previous video, BaCl2, which you know should be barium chloride, very often becomes written as well. Why don't I just call it barium dichloride? Because there's two chlorides. And the reality is you don't do that because this is ionic. Ionic compounds don't get prefixes. Only covalents do. Okay, finally, the last type of naming. Now, these are a special type of ionic compound. It's a very special type of ionic compound, and acids are ones where the plus, the cation is hydrogen. Okay, that's the main way, or probably the most significant way that these guys are unique. It's because the cation. Sorry about that. I had to hit the cough button. I had a little tickle in my throat. So in these compounds, the hydrogen is the cation. Just makes it easier. It's still ionic, still charged particles, but it still has ions. So, like HCl, the H has a +1 charge, chlorine. So if it wasn't in an aqueous solution, which is the other part of the problem, if it wasn't in an aqueous solution, then the other headache would be, I can do the shoes. Then if it wasn't dissolved in water, then it would just be hydrogen chloride. But since we're talking about this being dissolved in water, we're going to name it a little differently because it's an acid. Or H2SO4. That would be hydrogen sulfate if it wasn't dissolved in water, but if it is dissolved in water, it has a different name. Or H3PO4. If it wasn't dissolved in water, it'd be called hydrogen phosphate. But because it is dissolved in water, it's going to get a different name. So let's talk about how to name these. So first off, there's two main types of acids. There's binary and what's called ternary. Binary is when there's just two atoms, like hydrogen plus one other element, like the HCl, the HBr, HI, H2S has hydrogens plus one other element, not with a polyatomic ion, just with a monatomic anion. Well, the way we're going to name those is with the prefix hydro. Hydro, something in the middle that will give us the essence of what that element is, and ic acid on the end. So, for example, HBr would be hydrobromic acid. Hydro in front to tell me it's a binary acid, and brome in the middle saying the other atom is bromine. Or another example might be H2S. H2S has hydrogen with sulfur. So I need to have some way to say sulf with an ic acid on the end. So it becomes hydrosulfuric acid. That's the name of that compound. So anything that's binary is going to have that hydro out front and is going to have ic acid on the end. Hydro out front is only used for binary acids. For ternary acids, ones where the hydrogen is attached to a polyatomic ion, we're going to name those a little differently, but we're not going to use the hydro prefix. We're still, in some cases, going to use the ic acid. That was just a fly or a gnat or something flying by there. Sorry about that. But we're going to change the ending to dictate what type of a polyatomic we have. Now, I already said on the previous video that most of the polyatomic ions end in either ate or ic. So we're going to use that as our indicator as to how to name the acids. So if the polyatomic anion ends in ate, then we're going to do ic acid. And a way to remember that is the normal mnemonic is I ate something and it was icky. Ate, ic. So for example, Oh, sorry, I should have done it. I ate something and it was icky. Ate, ick. So, for example, hydrogen sulfate, 8 is on the end of the sulfate, it becomes sulfuric acid. Or hydrogen with a phosphate ends in 8, ate something and it was icky, it becomes phosphoric acid. What if it ends in the other example, the ites? Well, if it ends in ites, then what we're going to do is we're going to use the us acid example. Okay, another way to a weird mnemonic to remember for that is Sprite is delicious. Ite us. Sprite is delicious. So you have hydrogen with nitrite becomes nitrous acid, and hydrogen with chlorite becomes chlorous acid. Ite becomes us. No hydro. Hydro is only used for binaries. So the last thing I want to share is a chart talking about how to name binary compounds. And you always ask yourself, if you have an ionic compound, okay, do you start with a metal? Okay, metal. Is it a main group metal? Then you're going to go ahead and use the name of the metal. If it's not a main group metal, it's one of the ones that has multiple charges, then you need to figure out what the charge is and make a Roman numeral. For the non-metal, is it monoatomic? Yes, then you just tack on the IDE. And then if it's not monoatomic, it's polyatomic, you're going to go use the polyatomic ion table that I shared with you, or in your textbook, it's tables 2.2 and 2.3. As far as naming acids go, hydrogen, you're going to name if it starts with an H, you figure out, is it with an oxyanion? Those are the ones that have polyatomics. Then you use 8 or 8 or ide. Okay, so it also is a gas. We're going to talk about that in a second. If it's a gas, that means it's not dissolved in water. Then you've got hydrogen ions, so it becomes hydrogen nitrate. Okay, it means it's not dissolved in water. If it's not dissolved in water, it doesn't get the acid name. But if it is dissolved in water, then it's going to get if it's 8, it's going to be icky. If it's us, it's going to be Sprite is delicious, going to be us. And if it happens to be binary, then you're going to use the hydro in front with the ick ending. And that's it for this video. So at this point in the game, we are done with chapter 2. So we are also done with the first unit. So we're going to have a test in a couple days. I'm going to give you an overnight or so in order to work on it. That will incorporate everything from chapter 1 and chapter 2. So this is your first assessment, your first real assessment within Chem 2. Again, that will come in a couple days. We'll have one day to kind of practice some of the wrap-up stuff in our synchronous time. But until then, you should be working on the chapter 2 homework to the best of your ability and bring those questions to our synchronous time. I would like to get a little more back and forth in response where you're a little more engaged in the synchronous time so you can get your needs met. But until then, next time, I will see you in the next video where we will start stoichiometry, chapter 3. Toodles.